From the swirling arms of distant galaxies to the expanding eye of a massive hurricane, spirals dominate the natural world. Many assume these patterns are a direct product of the famous golden ratio or the Fibonacci sequence. However, the iconic chambered Nautilus shell is rarely a true golden spiral, despite its popularity as a textbook example. The geometry seen in these dramatic spirals stems from a dynamic equation of physical motion, rather than a fixed ratio. We can model this using the complex exponential function, e to the power of I times x. As the value of x increases, the point orbits the origin at a constant distance, tracing a perfect circle. While this equation creates a perfectly balanced loop, wild natural systems rarely stay in such a state of frozen equilibrium. What happens to this mathematical system when an object is growing and spinning at the same time? We introduce a real component, the variable a, changing the equation to e to the power of a plus I times x. The imaginary part of the exponent, I times x, remains responsible for the rotation. The newly added real part, a, dictates exponential expansion, providing a constant push away from the center. These simultaneous forces of spinning and expansion break the circle, charting an endlessly expanding logarithmic spiral. This differs from an Archimedean spiral, where the distance between the rings is constant, much like a coiled rope. In a logarithmic spiral, the distance between the lines increases exponentially with every rotation. This exponential growth factor allows biological and physical systems to scale their volume without crowding their own center. The Nautilus builds progressively larger shell chambers to house its growing body, while maintaining a constant rate of rotation. Gravity and immense momentum cause a spinning galaxy's glowing arms to sweep exponentially outward into the surrounding dark void. Because a hawk keeps its prey at a fixed angle to its line of sight, its descent naturally follows a spiral. Despite differences in size and material, these systems all execute the same command of growth and motion. Jacob Bernoulli called this the marvelous spiral because it possesses a unique geometric property called self-similarity. Since the growth rate is constant, the spiral's fundamental shape never changes as it expands. Whether you zoom in to its center or out toward infinity, the proportions of the curve are locked in stasis. This self-similarity allows a system to grow infinitely large without the energy cost of altering its foundational structure. Physical systems do not plot points on a graph or understand the mechanics of calculus. As angular momentum and expansion reach equilibrium, nature follows the path of least resistance by growing without changing shape. This specific path of least resistance is what the complex exponential function e to the power of a plus I times x models with precision. This complex exponential function serves as the coordinate map for this specific recurring geometry of motion.